Unit 11, Day 5, Application of Quadratic Functions. Up in R12, and we're going to go over Lesson 5, the last one for Unit 11. So problem number 1, these are applications. Unless you work for NASA, your boss is probably never going to just hand you an equation. Instead, he's going to describe a problem. So here is a word problem. Now it does have an equation embedded in it, and that is a quadratic equation in vertex form. So Mr. and Mrs. Worthen are playing volleyball. Mr. Worthen hits the ball to Mrs. Worthen, and the arc of the ball can be modeled by the function f of x as given, where x is the horizontal distance in feet from where Mr. Worthen hit the ball, and f of x is the height of the ball in feet above the court. So first we're going to graph the function. What we know already about this function. This is a real-world application. So if x is our distance, when he first hits the ball, that's distance 0. So while the function itself will have values before 0, negative values for x, in the real world, we don't go back in time, and we hope that he doesn't accidentally hit the ball behind himself. So the next thing we know, the vertex, HK, is our vertex. So we know 2, 8 is part of the solution. If we put in 2 for x, 2 minus 2 is 0, 0 squared is still 0, times negative 1/2 is still 0, and f of x is 8. If we put in 0 for x, 0 minus 2 is negative 2, negative 2 squared is 4, negative 1/2 times 4 is negative 2, negative 2 plus 8 is 6. If we put in 4 for x, 4 minus 2 is 2, 2 squared is 4, negative 1/2 times 4 is negative 2, negative 2 plus 8 is 6. Parabolas are symmetric about the vertex. So let's go ahead and plot these 3 points first. We'll plot 2, 8. 1, 2, 3, 4, 5, 6, 7, 8. We'll plot 0, 6. And we'll plot 4, 6. Now we need to keep going to the right. So we'll go ahead and we'll try another even number, since we're going to have to multiply by a half at some point. So we'll put in 6 for x. 6 minus 2 is 4. 4 squared is 16. Negative 1/2 times 16 is negative 8. Negative 8 plus 8 is 0. At 6 feet, the ball hit the ground. 1, 2, 3, 4, 5, 6. And then we will connect our dots. I'm going to go ahead and show that if this was not a real-world condition, the ball would continue passing through the ground, and there would have been an arc on the other side behind Mr. Worthen. So it would have been a perfectly symmetrical parabola about that vertex. So we've graphed the function. What is the domain and range? Well, this parabola itself, the equation, x is unconstrained. So the domain would be all real numbers. But like we said, this is the real world. In the real world, we start from the initial hit of the ball at time 0. So my domain will be from 0 less than or equal to x, less than or equal to the distance when it hits the ground, 6 feet. Because the ball will not penetrate the ground, especially with an arc like that, a little blob. It will not go past through the ground and continue through into the liquid hot magma below. Our range. Well, our range, the highest point we get is this vertex. So x is less than or equal to 8. Or excuse me, y is less than or equal to 8. This is our range. So y is less than or equal to 8, our vertex height. And what is the lowest y can be? Well, in the real world, it hits the ground. So the lowest it can be is 0. So 0 less than or equal to y, less than or equal to 8. Maximum height of the volleyball is that height at the vertex, 8 feet. From what height is the volleyball hit? Well, it was hit at, the distance from him was 0. That's when his hand touched the ball. And the height at that point was 6 feet. How far away from Mr. Worthen does the ball reach its maximum height? Well, he hit it at 0 distance from him. 2 feet further down the court, it has reached its maximum height. So it is 2 feet away from Mr. Worthen at that point. If Mr. Worthen does not return, if Mrs. Worthen does not return this fierce spike, well, it's really more like a bump, hit by Mr. Worthen, how does his shot go? It would follow this parabolic trajectory and would hit the ground 6 feet away. And then bounce, but we don't model the bounce. If Mr. Worthen is standing 4 feet away from the net, which has a height of 7 feet, will the volleyball clear the net? If we take a look back at our table, 4 feet away, the ball was only 6 feet up in the air. So, no, it will not clear the net. What is the height of the ball after it has traveled 5 feet horizontally? Well, I didn't put that one in my table, so we will put 5 in for x, -1/2, times x minus 2, quantity squared, plus 8. We're going to put 5 in for x. Five minus 2 is 3. Three squared is 9. 9 times -1/2 is -9/2. -9/2 plus 8. Well, 8 is really 16/2. We have to have a common denominator to add or subtract fractions. So -9/2 plus 16/2 is 7/2, or 3 1/2 feet. Next problem. Ms. Babbitt and Mrs. Powers are also playing a feisty game of volleyball. Ms. Babbitt's shot can be modeled by the function h of t equals -t squared plus 2t plus 8, where t is time. So this is our new x. We're using t for time instead of x for distance, horizontal distance. And h of t is the height of the ball at a given time t. We're going to graph the function. So we'll go ahead and write a t-table again. In this case, it is a t-table of t and h of t. So first we'll put in 0. At time 0, the instant she hits the ball, we have -t squared. 0 squared is 0, -0 is still 0. Plus 2 times t, which is 0, which is also 0. And then we add 8. So at 0, we have 8. Time 1. -t squared. -1 squared is -1. Plus 2 is 1. Plus 8 is 9. By the way, this is also our vertex, which we can find by using vertex, maximum height, our vertex. The x value of our vertex, or in this case the t value, is -b divided by 2a, which means it is -2 divided by 2 times -1. b, a, -1. So -2 divided by -2 is 1. So our time at vertex is 1. Then we have symmetry. So at time 2, 1 second before this, it was at 8 feet. 1 second after this, it will also be at 8 feet due to symmetry. Then we'll put in 3 for t. T squared is 9. -9 plus 6 is 7. Correction. -9 plus 6 is -3. Plus 8 is 5. Then we'll put in 4. T squared, 16. Negative 16 plus 8 is 0. It has now hit the ground. So we'll go ahead and plot this. At 0, we have 8. 1, 2, 3, 4, 5, 6, 7, 8. At 1, we have 9. At 2, we have 8 again. At 3, we have 1, 2, 3, 4, 5. And at 4, we have 0. So here is our real world portion of the path. And then if you want to think about it, just theoretically, it would pass through and it would be symmetrical. On the other side. So domain and range. Well, like we said, real world, our domain, our values for time. T has to be greater than or equal to 0 the moment she struck the ball, up until the moment when it hits the ground, which is at time 4. Range. Well, our apex, or our vertex, is at 9. So 9 is the greatest value for h of t. And although in the theoretical side, we can see that it would keep on going down through the liquid hot magma to the core of the Earth, the ball's not really that heavy and it's full of air. So at this point it would bounce. So our height, minimum height, is 0. For what height is the volleyball hit? Well, that's the moment of impact. Has a height of 8, which means she jumped up, which is a good serve. And when does we already did the vertex, that was 1, and then we plug 1 in for t, and we get out 9, so our vertex is 1, 9. When does the ball hit the ground? When the height is 0, it is 4 seconds after hit. How far does Ms. Babbitt's shot go? We know how high it went. It went up to 9 feet high. It went down. But we don't have a horizontal distance formula for this, an equation for this. All we have is a height equation. So really, we don't know. There actually is a way, if you could calculate using gravity, to determine based off of a 4-second hang time how far that would have gone, but we're not going to go into that level of detail. Next problem. Tacoma Narrows Bridge in Washington has 2 towers that each rise 307 feet above the roadway and are connected by suspension cables. Each cable can be modeled by the function given, where x is the distance from one tower in feet and f of x is the height of the cable above the roadway. What is the distance between the 2 towers? Well, first let's draw a picture. That's not great. Let me draw a better picture. So here is our tower, 307 feet high on each end. Here is our beginning, x equals 0. Now we have a little advantage here. This equation is written in vertex form. So we know that the vertex of this parabola is 1400, 27. X equals 1400. And the height is 27 feet above the ground. So this isn't to scale. But what do we really know then? Well, if it's 307 feet high on the left and 307 feet high on the right, this is the vertex, which means it is exactly in between the 2 towers. So if the exact middle distance between the 2 towers is 1400 feet, then I also have another 1400 feet to the second tower. So although it looked complicated, the math is really pretty easy. It's 2800 feet. And that is the end of today's lesson.